Okay, so welcome to the lecture of this finite volume method, and we will start with a new topic on gradient calculations. And before moving there, let me just start with what we have done till the last lecture. And if you recall this particular page, this is where we stopped. When we are talking about the diffusion system, we are talking about the discretization of the diffusion system. What we have considered steady state diffusion system with source term, and then we started with Cartesian system, Cartesian orthogonal, moved to non-Cartesian orthogonal, then non-orthogonal unstructured system. And in each of these respective system, we have talked about the discretized equation, which actually looks like a equation of this nature, which is a same looking equation for all these different systems. What it differs is that when you move to one to another system, these coefficients will vary, and the contribution at the source term level, that also changes. And one important thing that you have come across, that when you deal with non-orthogonal unstructured system, you come across two important quantity, is the contribution due to cross diffusion term, and which actually leads to some sort of a difficulties in doing the calculation, because the cross diffusion term, if you recall it from our previous lectures, cross diffusion term you cannot calculate using the nodal values between the cells. That means if you have the cells like this and using these nodal values, you cannot actually calculate the cross diffusion term, and that happens with the increasing, and the cross diffusion term is actually increases with the increasing level of non-orthogonality. So that is why the non-orthogonal system brings some sort of an complexity in handling the process, but at the same time the beauty of this particular discretization scheme or the method is that you deal with a similar set of expression for all the node, and this gets modified when you move down to the boundary node, and the extra term that arises at the non-orthogonal system, if you make them 0, you move towards this side. So you can bring back your Cartesian orthogonal system. So the whole idea is that from the programming point of view, and also one thing that we have considered is the anisotropic diffusion coefficient. So all these things, if you make them simpler or assign certain values, it can get back you the simple Cartesian system. So the beauty of this discretization is that you can have a generic code which can be used for both Cartesian system, orthogonal system and non-orthogonal system. When it be used for the orthogonal system, the extra term like cross diffusion term, skewness approximation, all these should be made 0, then it is a special case and should be treated as an orthogonal system. And when the anisotropic diffusion values are assigned to 1, this could be treated as isotropic diffusion. Now all this process, while doing this diffusion discretization, the one important quantity is the gradient. So gradient is another quantity, the calculation of gradient is also very important. And why it is important? Because the discretization of gradients of phi at cell centered and faces are any fundamentals to construct the discretized set of diffusion equation. So essentially the gradient is fundamental to any discretized diffusion equation. So that is the important thing that you have. So that is why now we move to the calculation of the gradient, and we will look how or analyze how one can estimate these gradients for different kind of scenarios, and how that helps to be used in a discretized diffusion equation. So, this is how we are moving, and if you follow the things in a particular fashion, you can notice, or one can notice, that we are slowly building one step in the top of the other one. So, first we have discussed general discretization, now we have picked up a term by term discretization. For that we have started with the diffusion system. Now, the diffusion system requires one important quantity which to be calculated is the gradient. Now, in addition to that, when you deal with the fluid flow problem, so fluid flow problem means you will be dealing with Navier-Stokes equations, that also requires some gradient calculation in terms of pressure gradient, your convection term gradient. So, these are also there. So, but this requires different technique for calculation. So, that is why it is not going to be discussed explicitly those pressure gradient term or convection gradient term, but essentially the normal gradient calculation, that means let us say del phi calculation in a diffusion system, that we will start with. So, to start with, we first start with a one dimensional problem. So, let us look at this one dimensional problem. You have a cell here, and this is the basically cell boundary. So, they are delta xc apart. So, the width of the cell width is delta xc, it is in the 1D, and the east node is E and the west node is W. So, this is also one can think about 1D uniform, that means delta xc equal delta xe, it must be equal to delta xw. So, they are same. So, the cell width is kept same, and as per our general convention, the face which is connecting the point C and E, or the element C and E, is small e, and this distance is delta xc, and the connecting faces between west and C is small w. So, these are the notation, and the direction is defined in x direction. So, what we want to calculate is that d phi by dx at the cell face E. So, that is what we are always interested in, to calculate all these fluxes at the interface. In order to do that, what we need to do? We use the information from the cell values, and this should be xc minus xc. So, one can write that is phi e minus phi c divided by del x e. So, can be, so now one can also write that d phi by dx at cell center C. So, this is a value which is at the centroid of that element C. How you can do that? Now, previous calculation we have used the value at the cell center and calculated the value at flux phase E, and similarly one can find out at phase W. Now, in the reverse calculation, what we want to do? We want to use the information of these phases like E and west phases and try to calculate the derivative at centered C. So, which can be written at phi E minus phi W divided by x E minus x W, which one can write that phi E plus phi C by 2, which is basically again an linear interpolation between the information of C and E, and linear interpolation between C and waist divided by delta xc, because this distance is delta xc, which one can write phi e minus phi w divided by 2 delta x c. So, this essentially means that they are of the central differences scheme. So, usually referred to as central difference scheme. So, the central difference which we now find out at cell center C, we using the information of east cell and the waist value, it is essentially one can refer as central difference, and this is going to be the derivative or the first derivative using central difference scheme. Now, for Cartesian grid in multiple dimension, the derivatives can be also computed by applying the same principle. So, now if we move to Cartesian grid, the same derivative can be applied using the similar principle in the respective coordinate system. So, now let us consider this two dimensional, this is a 2D Cartesian grid. So, now if you consider this 2D Cartesian grid, and this is a very well known or familiar figure that we have been using so far. It is a standard cell center C, east node is E. So, this face would be E, north face N, west face W, south face S. These are the cell vector or the surface vector at E face, surface vector at the north face, surface vector at the west face, and surface vector at the south face, and the other nodes like north, northeast, southeast, south, southwest and northwest, and these are the respective cell distances in x and y direction. Again, this is also uniform in each direction, so that delta xc or delta xe, they must be equal. So, using now these particular things, one can also look at the calculation of this first derivative at the cell center. So, this would be phi e minus phi w divided by xc minus xw, and this is in this direction of x or x direction. Now, it is in the two dimensional system. So, we need to get an estimate in the other direction or the derivative in the other direction. So, the first derivative in the y direction would be phi n minus phi s divided by xn minus xs. So, one can think, now consider these three elements in one direction and similarly obtain the derivative at cell center, but now the derivative along this direction. So, that uses the information of north cell and the south cell. So, this is quite straightforward, and if you have in 3 dimension, similarly one can compute in z direction. So, that would be quite straightforward. And why that looks so straightforward? It is a 2 dimensional uniform Cartesian system, and obviously they are orthogonal to each other. So, once you do that, now we want to use the different techniques, like one of the very famous technique is that Green-Gauss gradient calculation. So, that means this is very or common or widely used methods for computing. So, it is widely used method for computing gradients. So, that essentially used in very commonly in CFD codes. So, this has already been discussed while we are talking about the discretization of the diffusion system, but the final form of the equation now we will discuss in details. Now, if you look at it, the mathematical expression for that remains like the del Bc of the Bc summation over all the phases, and that would be phi f or phi f S f, where f stands for phase and S suffix f is the surface vector. Okay. Now, the phase value phi f is still need to be calculated, or some formula needs to be used to calculate the phase value. So, there are two approaches which are presented. One is the phase based with a generally compact stencil involving the phase neighbor. So, one approach could be the phase based approach, which actually uses some compact stencil involving phase neighbors, and the second option could be vertex based. So, that is another option one can use, the vertex based, that with larger stencil, okay, which actually involves the vertex neighbors. So, essentially in all these approaches you need to have the information from the neighbors. Sometimes it is the phase neighbors, sometimes it is the vertex neighbor, and also the number of cells in this extended stencil is about twice the one which required for the phase based. So, the use of compact stencil, that the phase based approach is quite attractive with implicit methods, because it leads to more compact Jacobian matrices. However, this larger stencil that involves the vertex neighbors, that brings some more information into the reconstruction, and therefore it is expected to be slightly more accurate. So, as soon as you say that, it means whenever you use different kind of approach, always it comes with some sort of advantages, some sort of disadvantages. Now, first thing that we will start with is the calculation based on, so first method. So, the method 1, and method 1 is we use the compact stencil, and what is that? So, here is the picture of that, it is again 2 dimensional, and this is a face which is connecting the points with the neighboring cell F, and as usual the connecting line between C and F belongs to E, and these are the from the reference frame, the distance vectors for C is RC, then this F is RF, the distance vector to capital F is R capital F, and the connecting point which touches the face is small f, and SF is the surface vector. Now, you need to calculate the phase value phi f, and one simple approximation would be using GC phi c 1 minus GC phi f, where again GC is the geometric weighting factor. Okay. So, once you use that information, then what you get is that calculation of GC. So, that will become now magnitude of Rf minus R small f divided by R capital F minus Rc, which is dFf, because Rf minus Rf will give dFf and Rf minus Rc will give dFc. Okay. So, R here is essentially represents the position vector, okay, and d is distance between points. So, that is what we get. Now, if the face is located at midway, that means at the middle of that, this phi f could be phi c plus phi f divided by 2. Now, this approach is quite simple to implement, and top of that, and simple to implement in 2D and 3D, and all operations which are involved are phase based, not requiring any additional grid connectivity. So, that way it is very straightforward. And secondly, this is also second order accurate. So, the order of accuracy is also high. Now, the other thing which is there, that when the segment CF and face SF intersection point coincide with the centroid of the face, that F, thus a second order accurate representation you can always obtain. Now, this condition is not usually satisfied with a general unstructured non-orthogonal. So, this is not be easily satisfied for a general non-orthogonal structured or unstructured system. So, that means essentially if you have some skewness in the system, whether in 2 dimensional or 3 dimensional, this simple calculation would not happen. And if you look at this particular 2 dimensional grid, again this is 2 dimensional face, 2D face, but it is non conjunctional face. Okay. So, that means there are some level of skewness present in the grid, which leads that the connections between C and F, that means the cell center of the concerned cell and the F, they are passing through the face at a point of intersection F prime, and the C which is touching the centroid of the face at point F. So, there is a offset between F and F prime. So, F here not equals to F prime. So, and the surface vector is acting at F, not F prime. So, there are multiple distance vectors which will turn out to be there. One is capital Rf, R small f, R F prime, R C, and this case now your calculation would be like the correction term would be phi f, which is equals to phi f prime plus some level of correction. So, that is what is required, because now f and f prime are not situated or located at the same point. So, once you have that correction, you can expand that and get del phi dot Rf minus Rf prime. Now, one can expand this one. So, if you expand this one in more convincing form, you can get at the face value phi f equals to G C phi C plus delta phi C dot R f minus R C plus second component which will come from 1 minus G C into phi f plus delta phi f dot R f minus R capital F. So, these are the two terms which you get after invoking the correction due to skewness. So, once you do that, what you finally get is that is equivalent to phi prime plus G C delta C dot R f minus R C plus 1 minus G C delta phi capital F dot R f minus capital F. So, this term which you look at it, if you compare with this equation which is phase value phi f, this is essentially the term which one can think about the correction term associated with this one. Now, what happens here is that G C, now since G C strongly depends on F prime, which indicates that the improved estimation of the gradient can be obtained through some iterative process, because G C is now cannot be evaluated in a algebraic fashion. So, that is why there is a dependency on location of F prime. So, at each iteration the average value at phase is computed using gradients which is calculated in the previous iteration. So, these phase values are then used to compute the new estimate of the gradients. So, if you do enough number of successive iterations and then which can actually can cause some oscillations, and usually not more than 2 iterations are performed because of this. So, what it requires, the calculation of G C which requires location of intersection point of F prime between C f and S f. So, now that is what it requires. So, essentially the calculation of G C which requires locating the intersection point F prime between C f and the face S f. For that purpose now you need couple of options. So, thank you. We will discuss other things in the next lecture.